Find all the real zeros of the following functions. So here are three examples. There's an f of x, there's a g of x, and an h of x. So we'll take a look at these one at a time. Let's call this first example A, example B, and then example C. Now the first one, look at the degree of f there. The degree of f is actually degree 4. So it's going to tell you a lot of information. Degree 4, that means if you have degree 4, well actually there's 2 here, and there's 1 here. I miscounted. The degree of f is actually 5. And I'm going to use a notation to symbolize that. I'm going to use lowercase, and then I'm going to use parentheses. And the degree of f is actually equal to 5. So that means it has the behavior of either positive x cubed, which is this, or negative x cubed, which is this one. So it also tells you your end behavior. And remember, the end behavior is simply the little arrows at the very, very end of your graph. Okay, the domain of any polynomial is all real numbers. So when we talk about the ends, we talk about the very far left and very far right, or very far left and very far right. So because it's degree 5, it either looks like an x cubed polynomial, or it looks like a negative x cubed polynomial. Since the coefficient is 2, we know that it actually looks like a positive x cubed polynomial. Now, this polynomial is in factored form. Remember, polynomials have this generic form. P of x is equal to a sub n x to the n plus a sub n minus 1, x to the n minus 1 plus a sub n minus 2, x to the n minus 2. And you keep counting down like this until you get a sub, let's say, 1, x to the first power, plus a naught, which is your constant. Okay, where the degree of this polynomial p is actually n, and n is a positive integer. Let's put all the details together and get an idea of what the zeros tell you. So to find a zero of a polynomial, we set the output to be 0, and then we solve for the x values. So that means 2 is not equal to 0. But however, we do have x minus 16 is equal to 0. Or what? Or x squared plus 4 is equal to 0. Or x plus 2. X plus 2 quantities squared is equal to 0. Okay. Ran out of room here, so let me clean up a little bit. I want to save room for all three examples. Okay. So you can see one of the zeros is going to be x equals negative 2. So x equals negative 2, x equals 16. This one here, this yields no solution, or no real solution. So we are done with the zeros here. Now this has degree 5. So with x plus 2, with the factor x plus 2 having multiplicity of 2, so this actually tells you a lot of information. It's a positive coefficient of 2, so you know its end behavior is going to look more like this one over here, the positive x cubed. So it's going to look like this one because we have a positive 2 here. So it's going to be more like a positive x cubed versus a negative x cubed. We have a 0 at 16. You could think of the zeros as x-intercepts. So if you have your x number line, you could think of 16 being way over here, and let's say negative 2 is over here. And we already know it's end behavior. So the end behavior is going down like this and then up like this. Because the factor x plus 2 has multiplicity of 2, this will actually not cross the x-axis. And it goes more like this. And there's only one more 0 going through 16. And so very likely this is a rough sketch of your polynomial. And if you want to see the y-axis, perhaps I could put it now right here in a different color. There's your y-axis. But remember, the zeros is analogous to finding the x-intercepts. Let's look at example B. Let's look at g of x. Can we find the zeros there? Of course we can. Once again, make sure your output is actually 0, and then we're going to solve for x. Now notice this polynomial can factor, and once again, we're going to have a multiplicity of 2 as well. So we have x equals 0, x equals 2 with multiplicity of 2. Now this time over here we had multiplicity of 2. That's my abbreviation for multiplicity. Multiplicity spelled out is this. Multiplicity of 2 here. What else do we have? We have x equals negative 2 with multiplicity of 1. So there are your zeros. Your zeros are right there. Now, how do we put this graph together? Well, g of x has this behavior. G of x has odd degree. So g of x has a degree of 5. So that means it's going to look like, actually, and there's a negative coefficient this time. There's a negative coefficient and has degree 5. So it's actually going to look like this one here, this end behavior, more like the opposite of x cubed. It's going to look more like that function. And if you draw the zeros, there's 3 zeros. They're evenly spaced, which is nice. So we have a negative 2, a 0 to be a 0, and then we have positive 2. Oops, I said negative 2. And it has negative coefficient and degree 5. Negative coefficient with degree 5. Which one had multiplicity? X equals 2 had multiplicity. So very likely it's going to come down this way. And it's going to go like this and like this. And because it's degree 5, you could do this. Yeah. So once again, this is a very rough sketch of g of x. You might want to ask yourself, how can you make this more accurate? And in short, you just simply pick more ordered pairs, right? You would just pick more ordered pairs. Let's look at example C. Example C also has degree 5, but negative 4, so negative coefficient. Notice the degree of h is once again 5. Oh, shoot. How come you guys didn't stop me? I made a mistake on example B. Example B doesn't have degree 5. Why don't we recount that? It actually has degree 4. Degree 4, no problem. We could fix that. It has degree 4. So if it's degree 4 and has negative coefficient, well, we actually have something else. This is going to look more like an upside down parabola, right? In other words, negative x to the 4th. No problem. We could fix that. Not a problem at all. There's a quick fix to this. That's what's that's the beauty of mathematics. It always tells you information. We can simply do that. And we need it to be looking more like an upside down parabola. So there we go. We just do that and we fixed it. Notice 2 still has multiplicity of 2. So it doesn't cross the x-axis. It's simply tangent to it. All right. Let's look at example C again. Degree of h is 5, and it is a negative coefficient. So it's going to look more like negative x cubed. H of x is going to look more like negative x cubed, and you can see its end behavior. Let's find the zeros. The zeros are going to be equal to negative 4x, x plus 1 times x minus 1, and then x squared plus 36. And we have what? X equals 0, x equals negative 1, and x equals 1. Once again, notice x squared plus 36 equals 0 does not yield a solution. X squared plus 36 equals 0 has no solution, or no real solution. Once again, we could actually sort of give ourselves a rough sketch of this polynomial x here. Once again, the zeros are evenly spaced. Remember, the zeros are analogous to the x-intercept. And everything has degree 1, so everything is going to cross the x-axis once. I should say the graph is going to cross the x-axis once at the 0. And it doesn't be tangent to it. So there isn't much of a choice here. So here's a rough sketch. Go once, and through. There it is. This is a rough sketch of who? This is a rough sketch of h of x. So that's really why you're trying to find these zeros. They really represent the x-intercept, and it gives you a better idea of how the polynomial is behaving. You want to go back and make sure you understand end behavior. End behavior is very important. Degree 4, what happens with the negative coefficient, what happens when you have a negative coefficient, what happens when you have a positive coefficient, and so on and so forth. I made a mistake right here. That says positive x to the 4th. That should say what? Let's fix that. That should say similar to negative x to the 4th. I meant to write the similar symbol and then write negative x to the 4th. Let's make that negative x to the 4th stand out. Beautiful. I need to circle my zeros for the example C. There they are. And you should indicate multiplicity if a particular zero has multiplicity. So notice x equals 2 here has multiplicity of 2. Should definitely mention that. So remember to write everything on your paper. Don't let anybody graph for you. Draw your own graphs. Use your own paper. Use graph paper as needed. All right. Keep up the good work. Find all the x-intercepts and y-intercepts of the graph of the function. So here are 3 different polynomials. We're going to go ahead and find all the x and y-intercepts. Let's start with the x-intercepts. The x-intercepts occurs when the output is 0, or the x-intercept occurs when y is 0. So we need to set f of x to be 0, and then we can solve for the x-intercept. Why don't we try factoring? 0 is equal to, 3 is a prime number, so I'm going to guess 3x to be in one of my factors. And we need to get 5. Let's see. I think a 4 would go here and a 3 will go here. And that should do it because I'm going to add 9x and take away 4x. And I have checked my factoring. That is 100% correct. So what do we have now? We have 3x minus 4 is equal to 0, or x plus 3 is equal to 0. So we have the x-intercepts are 4/3 and -3. That's one way to say it. Another way to say the x-intercepts is simply translate both of these into ordered pairs. So if you translate the x-intercepts into ordered pairs, it is often clearer, and it might be easier for a word problem. So 4/3 comma 0, and then what else do we have here? We have -3 comma 0. So that is another way of understanding the x-intercepts, is simply translating them to be ordered pairs. Notice it's best to write a complete sentence when you're trying to describe the x-intercepts. Now, if you translate it into an ordered pair, it's actually a little bit clearer. Let's find the y-intercept. So the y-intercept is when x is 0. So the y-intercept procedure is simply write f of 0. This time x is 0. So I need to plug in 0 whenever there is an x. And then we're basically looking for the output value, which is the y value. So whenever you're evaluating polynomials, just make sure you put parentheses. That's really important. Whenever you see an x, you're going to put parentheses. Oh, I forgot the square here. Parentheses, and then put in your 0. So don't forget your parentheses, minus 12. Not a total surprise, f of 0 is equal to -12. Now, how do you read this function notation? Well, I'm going to read this. It says a lot of information. It says the y-intercept is -12. And if you translate this to an ordered pair, it's actually much easier to interpret. We know that the x value is 0, and then the y value is -12. So you can translate it to be an ordered pair. You can go ahead and pause the video and attempt the next 2 examples. And if you are stuck, unpause the video and you could reveal the procedures that need to be written down. Once again, I'm going to go ahead and start with the x-intercept. The x-intercept occurs when y is 0. Here we have a greatest common factor of -3 times x. So what's left? X squared minus 8x plus 15. Aha. And then, of course, you react to this problem. Use all those years of factoring to try to get this factored. 5, 3, both of them have to be negative, or both of them subtraction symbols. That is checked. And notice we see that -3 can't be 0, or x minus 5 is equal to 0, or x minus 3 is equal to 0. And from here, we could definitely see the x-intercepts. The x-intercepts are... oh, I skipped one. How come you guys let me skip one? Shame on me. Which one did I skip? Let me go back and fit it in. -3 can't be 0, right? It's a negative number. The one that I skipped is the second factor called x. X is, in fact, equal to 0. So the x-intercepts are 0, 5, and 3. Now, once again, it's a little bit easier if you translate this into ordered pairs. because it's much easier to identify them. Plus, later on, you're going to graph them anyway. So it's almost better to translate your intercepts into ordered pairs. There you go. Example C. There are 4 terms. The degree of f is actually 3. In fact, I know it looks like this. It looks similar to what? Similar to the function called x cubed. We need to find I forgot to find a y-intercept to part B. The y-intercept is done. There's only one y-intercept, so I could actually state it. The y-intercept is also 0. You can see the confusion. And if you translate that to be an ordered pair, it's simply 0, comma 0. This time I actually want this 0. This one, x is 0. Yeah. There we go. You actually found it when you found the x-intercept. It was just a coincidence. So you could state the intercepts in English, or you could translate them into ordered pairs. Let's find the x-intercepts for example C. There's a nice pattern with these 4 terms. There's no greatest common factor, but there are some common terms in the first 2 terms, and there are some common terms in the second 2 terms. And that's what we're going to do now. We're just going to use a method called factor by grouping. And if you take away 4, what do we have left? We have x plus 5. And what are the common factors? The common factor now is actually x plus 5. So let's take out an x plus 5. And what are we left with? X squared minus 4. And of course, you just react to this and you keep factoring. That's a difference of 2 squares. And we have our x-intercepts. Our x-intercepts are, from left to right, we have -5, -2, and 2. Once again, it's almost better and easier to translate those into ordered pairs. So -5, -2, and then 2. And the x-intercept occurs when the y value is 0. We need to find the y-intercepts, the y-intercept. So no plural there when we're talking about y-intercept. Because you know that polynomials are functions. For every x, there's exactly one y. So if there's a y-intercept, there will be only one of them. How do we find y-intercepts? We need to evaluate at x when x is 0. So we need to evaluate f of 0 and find the output. In this case, it's relatively quick. You can see that it's going to be 0 plus 0 plus 0, and then minus 20. So the y-intercept is -20. Once again, almost easier to translate this into an ordered pair. And so either one of those are acceptable. And there you go, finding x-intercepts and y-intercepts of a polynomial function. Determining the end behavior of the graph of a polynomial function. remember the definition of a polynomial. It's actually p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1. And you keep counting like this until you get to a constant. So we can call that constant a naught. Where the degree of the polynomial is what? Where the degree of p is in fact equal to n, where n is a positive integer. Okay, so remember that a polynomial function doesn't have any square root symbols in it. It doesn't have any cube roots and so on and so forth. N has to be a positive integer. Let's look at part A. F of x is given to be negative x cubed. You just have to make sure the polynomial is in descending order. So we're looking for the highest degree here, and we're going to make note of that. The highest degree here is this term right there, and that's really key. So for part A, B, and C, we're just looking for the term with the highest power, and that's that one. And we do need the coefficient as well. For part C, it's a little bit tricky, but you could see that f of x is going to be similar to something. And what is f of x going to be similar to? F of x is going to be similar, that's the similar symbol, of 4 times x to the 4th power. Now I don't need to expand the entire thing to see that. You can see from the two factors and the two multiplicities, this is going to have an x squared, and this is going to have an x squared. So when I multiply the x squared and x squared, we get x to the 4th. I do need the coefficient of 4 though, because I need to know if this is positive or negative. Once you have that, I can also circle the first term here. That is in fact going to be the first term, or the term with the highest power or highest exponent. Once I have that, I could actually draw the behavior of this. We're going to say that here, why don't we say it this way? F of x is similar to the opposite of 3 times x cubed. And what is the end behavior for that? It goes something like this, right? I'm just going to draw the ends. And part B, f of x equals negative 6 times x to the 6th. What does that look like? That looks like negative x to the 4th. Once again, I'm just going to draw the ends. And because 6 is even, it looks like x to the 4th. Drawing just the ends here, the ends are going to go down on both sides. Who knows what happens in the middle? I don't know. It could do some stuff. But the ends are what you're focusing on. You're just focusing on the end behavior. And the last one here, if I just draw the ends, both of them are going up. Because you should know how to graph f of x equals x to the 4th as well, or g of x equals x to the 4th. So really, really focus on the ends. Let me highlight the ends here. So the end behavior, end behavior, end behavior, end behavior, end behavior, end behavior. Now we just simply match the description that's given. And there you go. We have matched the descriptions that are given. You could read these out loud to make sure. But the key here is actually just draw a quick sketch of the end behavior by noting the degree of the polynomials that were given. Inferring properties of a polynomial function from its graph. Below here are two examples. There's example A and example B. Both of them are called f of x, but clearly they are different polynomials. One of them has 2 zeros, and this one has 1, 2, 3 zeros. You can clearly see that they are different polynomials. So we'll look at these one at a time. Let's separate the page here. For part A, the function f is decreasing over which intervals? So we're looking at this function from left to right. It's very, very important that you actually copy this graph down on your own sheet of paper. And then draw the arrows, and then label the number line as well as you can. But more importantly, draw the arrow so that it matches the domain and range of the function. In this case, we are worrying about the domain in part A. Part A of A, I should say. The function f is decreasing over which intervals? Notice it's decreasing here. From negative infinity up to negative 9, and then it starts increasing. So when we're talking about decreasing, we're talking about decreasing from left to right. Now it's increasing, it starts decreasing starting at negative 6. So we're going to use parentheses, negative 6. It actually hits a peak when x equals negative 6. So we're not going to include negative 6, but as soon as you go to the right side of negative 6, it starts decreasing again, and it goes all the way up to 0. So let's fill in this bubble here. It's better to just write this out on your sheet of paper instead of trying to bubble things. Bubbling things does not help you learn, and it's almost better to write things out. Actually, I shouldn't say almost. It's always better to write things out. It also decreases from 5 to 8. So the next one is this one, 5 to 8 here. So for part A, I'm actually going to write this in a complete sentence. Part A of A, f is decreasing on the following intervals, and we can simply list them. Negative infinity to negative 9, negative 6 to 0, and then not negative 5, just positive 5 to 8. Okay, the function f has local minima at which x values? Where are their local minimums at which x values? You can see them from the graph. And so we have a local minimum at x equals negative 9. We have a local max at x equals negative 6. We have a local minimum at x equals 0. We have a local maximum at x equals 5. And we have a local minimum at x equals 8. So we're really concerned about the minimum values. And once you see the minimum values, then we read them. We read the corresponding x values. Here we go. Let's try this. So at x equals negative 9, x equals 0, and what? X equals 8, there are local minimums, or local minima. What is the sign of the leading coefficient of the polynomial f? In this case, f of x does look like a times x to the fourth, where a is positive. So the sign here is positive. Which of the following is a possibility for the degree of f? It looks like x to the fourth, but of course, any even degree for a polynomial will have similar end behavior. So in this case, our answer is going to be 4, 6, or 8, or 10, and so on and so forth. In this case, 4, 6, and 8 were the possibilities. So I'll go ahead and circle those. 4, 6, and 8. I'll write them bigger for you as well. And why don't you go ahead and try example B. You could pause the video and then check your answer towards the end by unpausing the video. First thing you want to do is actually redraw this graph on your own sheet of paper and make sure you draw arrows at the end of a polynomial to match the domain and range. For decreasing intervals here, we have quite a few intervals. If you're reading the graph from left to right, you're going to see that it's going for these two intervals here. There should be one more. Yeah, there's 7 to infinity. So it's better to write this out on your own sheet of paper. We could say f is decreasing on the following intervals. -9, -6, -2, 3, and 7, 8. Another good reason to write more notes or complete sentences in your homework is so that when you go back and study your homework, you should be able to memorize the instructions that were given. Okay, if you memorize the solution, then you might as well memorize the instructions to get the complete language. Okay. Part B here says the function f has a local maxima at which values. If there is more than one value, separate them with commas. I'm going to just go ahead and write a complete sentence in here. It'll be easier. At x equals -9, x equals -2, and x equals 7, there are local maxima. There are local maxima. Okay. Like I said before, it's better to just write them in complete sentences. It makes more sense. I'm just going back and circling some of those complete sentences. Helps you really understand vocabulary. What is the sign of this leading coefficient? We're on part C. Well, this actually looks like, this looks like an opposite of x to the 4th. Oops, that's not the opposite symbol. Meant to write the similar symbol first, and then we have negative, or the opposite of x to the 4th. So in this case here, the sign of the leading coefficient is negative. And we can write that in a complete sentence as well to learn the vocabulary. The sign of the leading coefficient is negative, and it will match the negative symbol in front of the x to the 4th. Which of the following is a possibility for the degree of f? It is looking like degree 4, and of course every even degree polynomial will have the same end behavior of x to the 4th. So in this case, it's actually the 3 even numbers that are given. If they gave you 10, 12, 24, 48, or 52, you would be able to select those even numbers as well.